In primary school and lower secondary, our students learn about different forms of energy, like heat energy, light energy, electrical energy, and so forth. They also learn how energy can be converted from one form to another. For example, when I drop this basketball, students will tell me that gravitational potential energy is converted to kinetic energy. And their responses usually end there. They are very familiar with different forms of energy, and the idea of energy conversion helps them make sense of what they see. But there are rich discussions related to disciplinary ideas in physics, such as interactions through forces and fields, that do not feature strongly enough. This brings me to a pedagogical framework involving energy stores and energy transfers. To facilitate our understanding of the framework, here are some teaching and learning manipulatives which I would like to introduce to you. Energy cubes and energy cards. This cube has 6 faces. Each phase represents a store of energy: chemical potential, elastic, gravitational, internal, kinetic, and nuclear. These energy stores can help us think about the amount of energy present in an object of interest at the beginning and at the end of an interaction more clearly and more actively, like in the case of dropping the basketball. This allows us to account for the total amount of energy in the system. For example, let's say this card is the object of interest. When it's moving slowly, I can use 2 cubes to represent the amount of energy present in the card. And I turn both cubes to show that these 2 units of energy are present in the kinetic store. When the card is moving faster, I can use 3 cubes to represent the total amount of energy in the kinetic store of the card. Besides these cubes, I also have cards to help us represent how energy is transferred from one energy store to another. Here I have 4 cards. Each one represents a different mode of energy transfer. I use this card to represent energy that is transferred mechanically by a force acting over a distance. For example, when I exert a force to push this card, I use this card to represent energy that is transferred electrically by an electric current. For example, when I close a circuit and the energy is transferred from the battery inside this torchlight to the light bulb. I use this card to represent the energy that is transferred through heating due to a temperature difference. For example, when I place a spoon in this hot cup of water. I use this card to represent energy that is transferred through propagation of waves, either mechanical waves like sound or electromagnetic waves like light. Let us see how to use the energy cubes and cards in a scenario. In my hand is a miniature card. It will be our object of interest. The surface of this track is very smooth, so we can safely assume that a negligible amount of energy is transferred out of the card through the work done against friction. Let me show you the motion of the card with me interfering midway through its motion. Let's take another look at it again, this time in slow motion. Here, the card moves along the surface at constant speed in its initial state. You can see clearly from the speed time graph that the speed is indeed constant. If you were to use the energy cubes to show the energy present in the initial state, I believe that you would turn the cube to show the kinetic store. At this stage, do not worry about the number of cubes needed to represent the total energy in the initial state, because I didn't tell you the speed of the card or the mass of the card. So let's set it at a small number like 2 cubes, which is manageable. This is only an arbitrary number. At the midpoint, when I push the card, you see it moving faster. The graph also shows you that this is true. What is the reason for this change? Some of us may say that it has more kinetic energy, that's why the card moves faster. However, this response would imply the kinetic energy was the cause of the card speeding up. In reality, it was the force that I applied on the card that was responsible for this to happen. I would also like to point out that the card accelerates because of the unbalanced force acting on the card. When a force from my hand moves the card over a distance, work is done and energy is being transferred in the process. So I can use this card. Energy was transferred mechanically from my hand to the card due to the force acting over a distance. Now is a good time for us to think about energy conservation. At first, you have 2 cubes showing the amount of energy in the kinetic store of the card. Then, more energy was transferred mechanically from my hand to the card. By how many units? To make it easy to manage, I will just use a small number, let's say 2 again. To represent this, I will introduce 2 energy cubes and cover them with this card to show that these 2 units of energy were transferred mechanically by a force. There is another way to think about this. At the start, we have a card moving at a constant speed. We assume that it had 2 units of energy in the kinetic store. To represent this on the chart, I will place 2 chips in column K. K stands for energy in the kinetic store. 1, 2. As it was moving, a force was applied on the card. We assume another 2 units of energy were transferred mechanically to the card by this force acting over a distance. To represent this, I will place 2 chips into this box on the map. In the end, there should be 4 units of energy in the card altogether. 2 units that were originally present in the kinetic store, plus 2 units transferred mechanically to it. All 4 units are present in the kinetic store of the card. This allowed you to account for the total amount of energy in the system. At the same time, the energy transfer card helped you to understand how energy was transferred into the system, which is the card. Look across these diagrams. Notice how the energy cubes, each represented by 1 chip in the kinetic store, help you to think about the amount of energy at the beginning and at the end of an interaction more clearly. Together, this enabled you to have a more meaningful and rich understanding of the interactions in this scenario. Let's do a quick recap of the energy stores and transfers. I hope you remember what they are. There are 6 energy stores: chemical store, elastic store, gravitational store, internal store, kinetic store, and nuclear store. They help us account for the total energy in the system, and there are 4 energy transfers. Energy transferred mechanically by a force acting over a distance, electrically by an electric current, through heating due to a temperature difference, and through the propagation of waves. They help us think about how energy is transferred and draw connections with the disciplinary ideas in physics. I hope you have a better idea of what energy stores and energy transfers are. It's time for you to explore more examples and familiarize yourself with the other energy stores and energy transfers which were not covered in this video. Have fun exploring!